a model for kinetics or the collision model. So for a reaction to occur, three conditions must be met. First, the reactants have to come into contact. Two, the collision has to have a certain amount of energy, and we know that energy as activation energy. And three, the collision has to have the correct geometry. So we'll look at each of those conditions. So first, the reactants must come into contact. Makes common sense, right? If you use your common sense, you'll understand it. The molecules have to collide in order to react, so they have to have the proper orientation. If the concentration of these reactants is increased, there's going to be a greater number of collisions, and you're more likely to get more product. So in the first slide, we have just a few reactants, and in slide B, the concentrations have increased, so you're more likely to have a successful reaction. In number 2, we have a couple of graphs we're going to look at in the next couple of slides. The collision has to occur with a certain amount of energy, and that minimum energy is known as activation energy. So understanding this graph is important in chemistry. Notice the vertical axis is energy. The reaction coordinate, it's kind of like the time that the reaction goes through. So of course you start with your reactants. They have a certain amount of energy. This activation energy is always located from the reactant line to the top of the bump, all right? And we abbreviate that activation energy. At the end of the reaction, that's where we have our products. And notice that that is how we calculate our change in enthalpy. This is an endothermic reaction, so energy has been absorbed, so your products have more energy than your reactants. So endothermic, remember that's a positive delta H. So activation energy goes from the reactants to the top of your bump. If it's an exothermic reaction, there's your reactants again. They start there. There's your activation energy. Goes from the reactants to the top of your bump. And then in this one, it's exothermic. So there's your change in enthalpy right here. And remember, that would be a negative enthalpy if you were writing it as delta H. An effective collision is when the geometry is correct. So when you watch these little circles and squares, notice that they only react when it's the proper orientation. They'll bump off each other, but it has to be the proper orientation for the reaction to occur. So our third necessary condition is that the collision has to have the correct geometry. So we're looking at a reactant here of O and Br, and this reactant, if the Brs collide, they'll come off. Our product is Br2 and NO. Notice if they collide and the Brs are together this way, head on, you'll still get your Br2 and you'll get your two NOs. So that's an effective collision because it has the correct geometry. If you have the incorrect geometry, so your oxygens collide, nothing's going to happen. They're just going to bounce off each other, so no reaction occurs. Another way to look at it, so here's the actual formula. I had it in a different order. You have the bromine, nitrogen, and oxygen all lined up. When you have an effective collision, this is your Br at this end. The Br can be separated, and you have your two nitrogen monoxide molecules. That's an effective collision. Remember here, that's where your reactants start. This is energy on the vertical axis. Remember this bump, you remember what it's called? Yep, activation energy. So it has to have that energy. It occurs, and then think about, is this reaction an exothermic or endothermic reaction? And if you said exothermic, you're correct because the products have less energy than your reactants. The next slide is just looking at it a little differently without our models. So there's your reaction progress. You can think of that as time. Here's your potential energy on the vertical axis. There's your reactants. There's your activation energy. For the reaction to be successful, it has to have that minimum amount of energy. The orientation is correct, and we get our two products. And there's our delta E, or you could be more specific and call it delta H, and we know it's exothermic because the products have less energy than the reactant.